Hi Year 7, so I'm going to give this a go and see if I can do some notes for you and some presentation for you via a video. This is my first time doing this and let's see how we go. Alright, so we're looking at machines, okay, and our first little part of machines is what can machines do. Okay, so let's jump in. And here we've got a set of diagrams, and these are really cool. These are from Da Vinci's work. Okay, and Leonardo da Vinci spent a lot of time designing machines. Okay, and this is what you might be thinking about when we start talking about machines, or you might be thinking about, you know, trucks and cars and things like that. And we're going to get to that near the end of the topic. Okay, but to get to that, we need to start with some very simple machines. Okay, and you can see here in the diagrams here that while we've got some really cool things like this, we've actually starting with really simple things like here's the wheel. Okay, and here he's talking about a lever. Okay, and another lever here, and here we've got a set of gears. And so what we're going to do is we're going to talk in this topic about the components that make a complex machine. And any component of a complex machine can be called a simple machine. And we're going to look at how they work. Okay? And what we'll do is we'll build that up to the idea of being able to make a more complex machine. So let's have a look at that now. Okay. And here we've got, alright, here's a very complex machine waiting to go. Alright, this is what's called a Goldberg machine, and I'll run the little video for you. Alright, well, while it's just loading for a sec, let's just pause and let's just talk about that first little idea there. And the video talked about the fact that we've got 6 simple machines. Okay, we've got levers, inclined planes, wheels, gears, pulleys. Okay, and you may have noticed that they are the headings in our book. Okay, so we're going to look at all these different types of simple machines as we go along. Right. But our end goal, and we're going to actually build one of these at the end of the term. Okay, we're going to have a whole day where we can work on our Goldberg machine and we'll be able to build something really cool together. To get to that, we need to know about all the different types of simple machines. Alright, so now I know it's really exciting to see all the cool gadgets there, but just remember this would have taken them months to set up, and we're only going to have a day. So we'll bring ours down and make ours a lot smaller. Alright, but that's the overall idea of what we're going to do, and we're going to look at all the different types of machines. Now, let's go on and talk about why machines are important. So, in your notes, you've got a flap section that's got what can machines do. So let's have a look. Okay, and you need to collect some pictures to go into your notes here. Alright. So the first thing a machine can do is it can change the size of a force required to complete a task. You can see here these two guys are trying to pull this really heavy load up this inclined plane. Okay, in fact, there's a machine there that's making it a lot easier, because if they have to get it all the way up to the top here of this blue section, it would be a lot harder to just lift it straight up. So instead they're pulling it up the side. Now to make it even easier, they're using a wheel. Okay, and they've actually got a little bit of a lever going on here that's helping them out to move the box up to a position where it's a lot easier to put the weight onto the wheel. Alright, and then they're providing force. Now, what the machine is doing is it's making the distance a lot longer, but it means that the force they both require is a lot less. Okay, so that's a really important component of a machine. Here's another example. We've got here a pulley system, and this is designed to lift heavy objects and then allow the user to move it around on the wheels really easily around a workshop. And that again means they can lift heavy things with very little force. You can go the other way, and here on this bike, the bike rider is providing a lot more force down than they would by just walking. But the result is that because they've given more force there, the wheels go around a lot faster, because the force here is being amplified to that distance there, and therefore they go much faster. You can go a lot faster on a bike than you can by walking, well, hopefully. Again, here we've got an example, a wheel rolling down a hill, and certainly it's faster to get that rolling action happening than to just walk down the hill. Right? It can also change the direction of a force. So here is a pair of gears, and these are called beveled gears. Right? And what this is doing is translating a force that is probably coming from this engine here, because in the background here you can see this water, and so almost certainly that shaft there is heading off to a water mill, a big wheel that's being pushed around by the water. But movement this way isn't very helpful. So what they've done is they've put a set of gears and they've translated it so that the motion is going around. Okay, and probably at some point in the past there would have been a large stone down here, and that would have turned round and round and ground up the grain into flour. Okay, this is an old flour mill. Okay, and here's another example of changing a force. Okay, you've probably seen these in the workshop. This is used to put a nut onto a bolt. Now the force you're going to apply is the nut is going to push down onto the thing. But to make it a lot easier, we're going round and round and round. And then to make it easier again, rather than trying to turn the little nut here, we extend the arm out and we give ourselves a lot more distance. You imagine going here, short distance, going the same amount, we're going a big distance here. Okay? But that means that because it's a bigger distance, it's going to be a smaller amount of force required to make the same thing happen. And that's why it's a lot easier to get a nut on or off a thread using a spanner. Okay, let's talk about what that all means, and I'll let this little video play out for you.
Eureka! The story so far. Machines don't reduce the energy you need to move things, but they can reduce the force you need. They do this by increasing the distance through which you exert your force. Oh, mechanical advantage and friction. Here are two scientists, Professor A and Professor B. They are both equally strong. And here is a very heavy book about science. We are now going to perform a scientific experiment. We are going to find out which of the two professors can lift the book with the lesser amount of force. First, Professor A. 24 newtons of force. Now, Professor B. Only, what? 6 newtons? Well, there's no doubt about it. Professor B is the winner. You're quite right. It's not fair. Professor B had an unfair advantage. He used a machine, a lever, to give himself a mechanical advantage, in fact. But just how much mechanical advantage did the lever give Professor B? It's easy to work out. Both professors lifted the book to a height of about 10 centimeters. Professor A lifted it straight up, so he had to pull against the full force of gravity, which was pulling the book down. But since Professor B's lever arm was 4 times as long as the arm the book was resting on, he only had to pull with 1/4 the amount of force, 6 newtons instead of 24. In other words, his input force was 6, and his output force was 24. And all you do to calculate the mechanical advantage of a machine is divide the output force by the input force. So Professor B's lever had a mechanical advantage of 4. You'd like us to repeat the experiment, Professor A? You think you can equal Professor B's feat of lifting the book with a force of only 6 newtons? Very well. Professor A is now setting an inclined plane against a block of wood 10 centimeters high. And the inclined plane is 40 centimeters long. Fine. That's 4 times the distance, so it should divide the force he needs by 4, which means that his Newton spring scale should read 6. What's this? 8 newtons? Well, there it is. Professor B is still the winner with a force of only 6 newtons, thanks to the mechanical advantage of 4 given him by his lever. Whereas with Professor A's inclined plane, we see that he has a mechanical advantage of only 3. Why is this? Why did the inclined plane have less mechanical advantage than the lever? Because of something we've forgotten about till now, the force of friction. Every time something rubs against something else, there's friction. In theory, Professor A should have been able to pull the book up the inclined plane with a force of only 6 newtons. But since friction was pulling in the opposite direction with a force of 2 newtons, the professor's pull had to total 8 newtons. Professor B, on the other hand, was lucky because the amount of friction between the point of the fulcrum and the lever arm is almost 0. So the lever is a more efficient machine than the inclined plane, because the inclined plane is plagued by the demon friction. But friction can be an angel as well, of course. Without friction between the tires of your car and the road, you wouldn't be able to drive. Or stop driving. Just as if there was no friction between the soles of your shoes and the floor.
Okay, so while that video is pretty old, it does give you a really good idea about what we're talking about here, which is mechanical advantage. This is why we use machines. So a machine will provide mechanical advantage. It makes it task easier. Alright? And as the video said, the mechanical advantage is the force that it should or is needed divided by the force you're actually required to use. Okay, and we can write that in this way. Alright? And we can compare two machines by comparing the mechanical advantage. Alright? Now, we're going to come back to that idea, and you've got a little flip out section on the right hand side there, And what we'll do is throughout the topic, as we finish looking at a machine, we'll come back to that little section there and we'll put a little summary of how we find the mechanical advantage of each type of machine, because they're a little bit different. So while they all work on the same rule, there are other ways of working out what's going on that sometimes are a lot easier, but they vary depending on the machine. Okay, so we'll put in some little hints for ourselves as we go along. Right. So I'm hoping that's going to give you some ideas about what we're going to look at in this topic. We're going to be talking about simple machines. We're going to be talking about their mechanical advantage and calculating the mechanical advantage. And we're going to see how we can apply forces in different ways to the process. Right. So with that, I hope this has been a nice little video for you. Thanks very much for listening.